You're listening to DTFHN for June 30th, 2026. I'm your duct-taped together host, Jack Hacksman. We're your daily tech feed for Hacker News, a website where everyone has an opinion and a GitHub link to prove it. Today smells like sovereignty and solder smoke. Breathe deep. Let's go. What does it actually take to go from zero hardware experience to a flying 8-motor drone? And more importantly, why does the answer matter for everyone who's ever talked themselves out of building something physical? Carolina Dubio wanted to do reinforcement learning on real hardware, not in simulation, not on someone else's platform, on a machine she designed and built herself. The octocopter isn't the point. It's the vehicle. Literally. She needed something that could lose motors and keep flying, so she'd have a meaningful fault tolerance problem to throw RL at. A quadcopter can technically survive a motor failure, but only by surrendering yaw control and letting the whole frame spin. An octocopter with 8 motors has enough redundancy that even with 2 motors down, in most configurations, it can still produce the full range of forces and torques. Normal, flight, full, authority. That's elegant engineering driven by a real constraint. Pull this thread a little further. She had no prior hardware experience. None. And she built the thing anyway. Designed the frame, selected the motors, wired the ESCs, figured out the flight controller, all of it. This is what builder culture looks like when the information is actually accessible. Every component datasheet is online. Every flight controller firmware is open source. The PID tuning guides, the motor thrust calculators, the frame design references. All of it sitting there, waiting for someone curious enough to pick it up. The craft here deserves specificity. Choosing an octocopter layout means thinking about motor placement geometry, because which pairs of motors you lose determines whether you keep full controllability. 2 motors 90 degrees apart, spinning the same direction. That's your failure mode. Everything else the remaining 6 can handle. That's not a guess. That's control theory applied to physical actuator redundancy. And she worked through it to make the RL problem well posed. One of the comments points out that octocopter is etymologically wrong. Helicopter comes from helicopter spiral wing, so it should technically be octopter. Fair. But the fact that the most substantive criticism anyone can find is a naming convention tells you something about the quality of the work. This is the kind of project that only happens when the tools are open and the knowledge is freely available. 10 years ago, building a custom multi-rotor required access to an aerospace lab or a very expensive hobby. Today, a person with no hardware background can design a fault-tolerant flying platform specifically to run reinforcement learning experiments on it. The sensors cost less than a textbook. The firmware is community maintained. The research papers explaining motor loss recovery are on archive. The tools exist. The knowledge is available. She picked them up and built something that flies. Now shift gears completely from autonomous drones to something beautifully low-tech. Because sometimes the most radical innovation looks nothing like what you'd expect. In Edun Sicilia, a British economist named E.F. Schumacher published a collection of essays called Small is Beautiful. His argument was simple and radical: that the developing world didn't need massive industrial infrastructure imported from wealthy nations. It needed what he called intermediate technology. Tools that communities could build, maintain, and repair themselves. The development establishment dismissed him. They wanted dams and factories and power grids. projects that required foreign engineers and created foreign dependencies. Schumacher wanted hand pumps and biogas digesting and solar cookers. He wanted sovereignty. Daniel Connell is working in that tradition, but with one advantage Schumacher never had. The internet, open source low tech, is exactly what it sounds like. Connell prototypes basic infrastructure, energy systems, water purification, food production, communications, using recycled materials and simple tools. Every design is open source, license-free, with full construction tutorials published for anyone to follow. The explicit goal is that everyone everywhere should be able to build and maintain their own infrastructure. One of the comments on Hacker News called the designs rather primitive and suggested the problem was aesthetic. That criticism misses the point so completely it almost proves the thesis. The constraint isn't what looks good on a product page. The constraint is what someone can actually build with materials available in their village, their favela, their off-grid homestead. That's not a limitation. That's a design requirement, and it's the hardest kind of engineering there is. This connects to something the open source world understands deeply: the Gingery Book. 7 volumes on building a complete metalworking shop from scrap have been quietly circulating since the 1970s. Open source ecology has been documenting the global village construction set for over a decade. Appropedia has thousands of pages of appropriate technology documentation. There's a long lineage here of people who understand that the most important technology isn't the most advanced technology. It's the technology you can actually control. The development industry spent decades building dependencies disguised as aid. Ship in equipment that requires proprietary parts, trained technicians, and a supply chain that runs through your capital city. When it breaks, and it always breaks, the community's right back where it started, except now they've lost the skills they used to have. Connell's approach inverts this entirely. Build it yourself. Fix it yourself. Teach your neighbor. The designs aren't primitive. They're sovereign. Moving on. The strongest case against private microreactors is straightforward. Nuclear has a 50-year track record of broken promises. NuScale canceled its first-of-a-kind project in 2023 after a decade of development. Westinghouse's AP1000 deployments at Vauxhall ran 7 years late and $30 billion over budget. The pattern is so consistent it might as well be a law of physics. Announce ambitious timeline, collect investment, miss every deadline, blame regulatory complexity. Rational observers would put Antares in exactly this category and move on. Except Antares just achieved criticality on the schedule they publicly committed to. In June 2026, exactly when they said they would. The clinical facts. Antares brought a non-light water, privately developed reactor to criticality at Idaho National Laboratory. It's the first time this has happened in the United States in over 40 years. The fuel is TRISO, fabricated by BWXT. The same fuel specification developed for the military's Project Pele program. The reactor was authorized under DOE's Reactor pilot program, which itself is designed to be a replicable licensing pathway, meaning the regulatory process Antares just navigated is explicitly intended to be used again by other companies. That last detail matters more than the criticality itself. Run this forward. If the licensing pathway holds, what Antares actually built is not just a reactor. It is a template. Every subsequent company that enters the Reactor pilot program inherits a demonstrated regulatory path. rather than inventing one from scratch. The single most expensive variable in nuclear deployment has always been regulatory uncertainty. The years of back and forth that balloon costs before a single watt is generated. A replicable pathway compresses that timeline for everyone who followed. The deployment target is electricity to a military installation by September 2028. The intermediate milestone is electricity generation in 2027. These are falsifiable commitments with dates attached, which is itself unusual in an industry that learned long ago to speak only in aspirational ranges. One note from the comments worth flagging. A reader identifies the reactor design as a pebble bed configuration based on the TRISO fuel, and asks whether there is reluctance to market it as such given Chinese progress in the same area. Fair question. China's HTR-PM pebble bed reactor connected to the grid in 2023. The engineering lineage here is shared. What differs is the deployment model. Antares is building transportable microreactors for distributed power, not gigawatt-scale grid plants. The reactor works. The timeline held. The pathway is documented. Everything else is commentary. Distributed power is one thing. VDOM, distributed intelligence, is another. Story 4. I've spent years watching the local model ecosystem follow the same pattern. A new release drops. Benchmarks look promising. You download it, you prompt it, and within 10 minutes, you're back to the API, because the thing can't hold a thought across 3 paragraphs. The gap between cloud and local has been, for most practical purposes, a canyon. Qwen 3.627b is the first model, where I'd say the canyon is now a ditch. The benchmarks aren't the interesting part. What's interesting is the failure modes. Or rather, the absence of the ones you've learned to expect. Ask it to write constrained poetry about quantum physics and dot dancing, and the chain of thought actually deliberates on rhyme schemes and physics terminology separately before combining them. Ask it to scaffold a hexagonal minesweeper with proper package management, and it does. First try, correct project structure, working code. These aren't frontier model achievements anymore. They're running on your laptop. That shift matters. Let's talk about the first principles here. What does it actually take to run a 27 billion parameter model locally? An 8-bit quantization brings it down to roughly 27 gigabytes of memory. You need a machine with unified memory architecture, which in practice means a high-end MacBook with 128 gigs of RAM. The article's author ran it on exactly that, and the thermal camera photos are, shall we say, educational. His knees were melting from the laptop heat. The comments section immediately and correctly pointed out that this machine starts at $6,700. So here's the comedy. The model is open, the weights are free, the inference server is llama.cpp. Open source runs everywhere. The quantization is community contributed by Unsloth. Every single layer of this stack is open, available, forkable, improvable. The only bottleneck is Apple charging you nearly $7,000 for enough RAM. The entire open source AI ecosystem has converged on a point where the limiting factor is a hardware vendor's pricing strategy. But zoom out 12 months. A year ago, the creative writing this model handles casually required GPT 4.5. A model you couldn't run, couldn't inspect, couldn't modify, and paid per token to use. Now the capability sits in a GGUF file anyone can download. That's the compounding effect of open weights and open tooling. Every optimization in llama.cpp, every quantization technique from the community, every architecture improvement from Alibaba's team. They stack, they compound, and unlike proprietary improvements, they compound for everyone. The hardware cost will follow the same curve it always does. Memory gets cheaper. Architectures get more efficient. The 27 billion parameter sweet spot today becomes the 70 billion parameter sweet spot on the same hardware tomorrow. The weights are already free. The tools are already open. The only question is patience. So open models keep getting more powerful. But what happens when governments hand your identity to the same gatekeepers we're trying to root around? One commenter on this story just dropped a link to an open-source decentralized identity system and moved on. No essay, no outrage, just... Here's the alternative. It works. It's open. That response tells you everything about where the real energy is on this problem. But let's talk about what the EU is actually building, because the architecture matters more than the politics. European governments are rolling out digital identity wallets. These are public infrastructure. The kind of thing you'll need to access government services. Verify your age. Manage credentials. They are, by design, something every citizen should be able to use. And the developers building these wallets in the Netherlands and Italy made a specific technical choice. They integrated Google's Play Integrity API for device attestation. Now, device attestation is a legitimate security concern. You want to know the wallet app is running on hardware that hasn't been compromised. Fair. But Play Integrity doesn't just check hardware integrity. It checks whether you're running a Google licensed Android. It checks whether the app was installed through the Google Play Store. It checks whether you're signed into a Google account. The security question. Is this device trustworthy? Gets bundled with an ecosystem question. Is this device ours? Take the stated principle to its logical end. If your public infrastructure requires Google's attestation, then Google decides who can participate in public life. A graphene user, someone who chose a privacy-respecting, de-Googled Android 4, gets locked out of their own government services. The EU built the Digital Markets Act specifically to prevent this kind of gatekeeping, then wired that exact gatekeeping into their identity layer. The technical alternative already exists. Android's Hardware Attestation API does the security checks at the hardware level without enforcing Google's ecosystem policies. It verifies the device. It doesn't verify the landlord. The engineering is there. Yeah, the choice to ignore it is a policy failure dressed as a technical requirement. This is public infrastructure. The attestation layer should be open, auditable, and vendor neutral. The hardware can confirm its own integrity. That's what secure enclaves and trusted platform modules were designed for. You don't need a platform monopolist to vouch for Silica. The tools exist. The open alternative is shipping. The question is whether governments will use it or keep handing the keys to the gatekeepers they claim to oppose. Moving on. A nonprofit wants to convince ICANN to give them control of .self, a top-level domain dedicated to self-hosting and human-centered computing. Their pitch includes one free subdomain per person, ethical hosting standards, and a decentralized identity layer. The application goes through ICANN's Applicant Support Program, which means reduced fees for mission-driven applicants. Sounds noble. Let me play devil's advocate for a minute. The strongest argument against this is sitting right in the Hacker News comments. Someone points out that the initiative's own PDF viewer redirects through Google Drive. The foundation advocating for digital sovereignty is hosting its manifesto on Google infrastructure. That's not a gotcha. It's a diagnostic. If the people building the self-hosting TLD aren't self-hosting their own documents, you have to ask whether the vision is ahead of the implementation or whether the implementation is the vision's confession. But here's where the devil's advocate falls apart. Every open infrastructure project starts with duct tape and borrowed servers. Linux ran on Minix. The first web browser was built on a Next workstation that cost $6,000. You don't wait for perfect alignment between your tools and your philosophy before you start building. You ship what you can and iterate toward coherence. The hypocrisy argument is a trap that keeps people from ever starting. The real question is economic. Running a TLD costs real money. Registry infrastructure, ICANN fees, abuse mitigation, DNS Anycast networks. One free domain per person is a beautiful sentence and a brutal business model. The doc called Qwen proved exactly this. Free domains attracted hobbyists, then attracted scammers, then got blocked by every major platform. The failure mode isn't technical, it's incentive design. What makes .self worth watching isn't the TLD itself. It's that someone is trying to encode values into infrastructure rather than policy. Policy gets repealed. Terms of service get updated. But if the architecture requires self-hosting, if the DNS layer itself is built around individual sovereignty, that's harder to undo than a blog post about digital rights. Will it work? Probably not on the first try. Maybe not on the fifth. But the attempt matters because it treats the naming layer of the internet as contested territory, which it is, and which most people have stopped noticing. The tools exist. The application is filed. Now, the hard part. Making free infrastructure that doesn't become a spam farm. We talked earlier about infrastructure. Nobody notices. Icons are the same way. Let's free those too. Every icon on your Mac dock is now the same shape. Every single one. Ask yourself why. Apple will tell you it's consistency. A unified visual language across platforms. And there's a kernel of logic there. Vision OS needs predictable hit targets for eye tracking. That iOS has used rounded squares since 2007. But macOS was always different. The Mac was the platform where an icon could be a pair of headphones, a construction crane, a literal bomb. Shape was information. You could find your app in the dock the way you find your car in a parking lot. Not by reading the badge, but by recognizing the silhouette. With Tahoe, Apple eliminated that entire information channel. Every third-party icon that didn't conform to the prescribed squircle got shrunk down and dropped onto a gray background. What developers are calling icon jail, the result is a dock full of identically shaped tiles where color is your only differentiator. If you have color vision deficiency, or if you just happen to use Slack and photos in the same session, good luck. The engineering question nobody at Apple seems to be asking is, what did uniformity actually buy? The answer, as far as anyone can tell, is nothing functional. It bought an aesthetic preference enforced through platform control. That's not design, that's policy. And the distinction matters because Apple has historically understood it better than anyone. The encouraging sign is Golden Gate. Apple's own team is walking back the worst liquid glass excesses. Sharper icons, less gratuitous translucency. That opacity slider that's basically a public admission the first version went too far. Credit where it's due. Recognizing a mistake and shipping a correction takes institutional courage. But the shape restriction remains, and this is where the open versus closed instinct reveals something real. When a platform owner dictates not just technical requirements, but aesthetic ones. When they punish nonconformity by literally imprisoning your icon in a gray box, they're treating the dock as their canvas, not yours. The Mac's icon tradition. Those gorgeous, distinctive, sometimes whimsical shapes that Rogue Amoeba showcases. That tradition was a form of Creative Commons. Developers and designers collaborating on a shared visual space. Free the icons isn't just nostalgia. It's a usability argument dressed in an aesthetic one. Shape is data. Removing it made every Mac harder to use. Put it back. So what happens when a developer looks at a framework everyone uses and says, actually, I can build something better? Story 8. Entire documentation, buried below the counterexample and the theme toggle. There's a single line about keys. Keys are unique across the entire render. 7 words that reveal a fundamentally different model of what a component tree is. In React, a key lives inside its parent. Move a component from one container to another, and React destroys the instance, kills the state, rebuilds from scratch. The key was a local address, and you left the jurisdiction. DTF treats keys as global identifiers. A component can migrate between parents, the way a musician moves between ensembles, carrying their instrument, their training, their memory of every note they've played. The identity belongs to the component, not to whoever currently holds it. This is a small architectural choice with large philosophical implications. React's model assumes the tree is the source of truth. The parent defines the child. DTF inverts that. The component defines itself. The tree is just where it happens to be standing. The library ships other ideas worth examining. Its memo only blocks the current component while children continue updating independently. Its context system requires no provider wrapper, no consumer boilerplate. A component simply declares what it offers, and descendants reach up and take it. Pull-based, not push-based. The distinction matters. Push systems require someone at the top to anticipate what everyone below will need. Pull systems trust the leaves to know what they want. Now, the comments on this post are worth reading carefully. One commenter identifies the poster as a bot. The introductory comment as generated text. Another questions whether a virtual DOM is needed at all in the current landscape. Both points have weight. The provenance of the code matters. Whether a human spent 6 days or a language model spent 6 minutes shapes how we evaluate the claim. But the design decisions embedded in this library are real regardless of who made them. The global key system, the pull-based context, the scoped memo. These are ideas that exist now in an MIT licensed package. Anyone can read, fork, and build on. The code is open. The concepts propagate. 1,000 engineers can examine these choices and carry the useful ones forward into whatever they're building next. That is how open source compounds, not through the authority of the author, but through the availability of the idea. Ideas propagate freely, but running them in production, that's where the real costs show up. What happens to a system when the person who built it leaves the room? This is an engineering question with a known answer. If the system was built to be understood, maintained, and owned by the people who depend on it, it keeps running. If it was built to be demonstrated, it stops working the moment conditions change. The article from Two Heads lays this out with unusual clarity. AI agencies sell setup. They show a demo where the agent reads, writes, updates, sends, creates. The input is clean. The path is happy. The client signs. Then reality arrives. Missing data, broken integrations, vague instructions, exceptions nobody documented. And suddenly, the system needs a full-time human just to keep it honest. The math gets worse. The old manual process persists because nobody trusts the automation. The new automated process persists because the company already paid for it. 2 systems, double the cognitive load, and a team that's now busy tuning prompts. Instead of doing the work the prompts were supposed to eliminate. The article calls this false productivity. Activity without value. Pull the lens back, and you see an architecture problem. These agency-built systems are closed by default. The client doesn't own the prompts, doesn't understand the integrations, can't debug the failures. When the agency moves on to the next sale, the client is holding a machine they can't open. That's not automation. That's dependency with extra steps. The honest path is smaller and less exciting. Pick one workflow, understand it completely before you touch it. Automate the part that genuinely requires no judgment. Keep a human where mistakes cost money. Measure after a week. Measure after a month. Build it like software, because it is software. Software that can drift, break, and produce confident nonsense. One of the commenters points out this problem predates AI entirely. Someone builds an internal tool, ships it, and inherits a maintenance burden nobody budgeted for. The technology changed. The failure mood didn't. AI works when you own it, when you understand what it's doing, why it's doing it, and what happens when it's wrong. The operating cost starts after the demo. That's not a warning. That's just how engineering works. We talked earlier about building foundations that last. Here's a story about building them safer from the start. In 1995, the Morris worm brought down roughly 10% of the internet by exploiting a buffer overflow in Fingered. The fix was straightforward. The lesson was not. 38 years later, we're still writing C programs that corrupt their own stacks. And we're still acting surprised when attackers notice. Philip Pislow looked at this situation and apparently decided the correct response was to make C memory safe, which is a bit like deciding the correct response to a house fire is to fire-proof wood. Criticality is a compiler that takes standard C code and enforces a capability model, so strict that dangling pointers stack corruption and use after free. Simply cannot happen. The latest target, set jump, long jump, and the uContext AP is. Context switching. The part of C where you save your entire execution state, wander off, and come back later, hoping everything is still where you left it. Pislow's own documentation calls setjump amazingly evil, which is the kind of honesty you get from someone who had to implement it safely. The problem is genuinely nasty. You call setjump inside a function, return from that function, and now your saved context points to a stack frame that no longer exists. In normal C, what Pislow calls YOLO-D with sec-C, this produces crashes so confusing your debugger can't even print a stack trace. In fill-C, you get a panic with a clear error message. The program stops instead of wandering into attacker-controlled territory. The uContext, AP, is our worse. You can create a context pointing to a stack, free the stack, then jump to it. Fill-C handles this by managing stack lifetimes itself, garbage collecting them when they're no longer reachable. The stack stays alive as long as any context references it. One commenter's reaction captures something real. They assume setjump and longjump were probably incompatible with memory safety entirely. That assumption is worth examining. We spent decades accepting that low-level control and safety are fundamentally opposed, that you pick performance or you pick guardrails. Fill-C is open source. The implementation is public. Anyone can read how stack lifetime tracking works, adapt it, build on it. The techniques Pislow developed don't have to stay in one compiler. They're patterns now available to anyone building tools. The ladder is right there. Nobody's pulling it up. This has been your daily tech feed for Hacker News for June 30th, 2026. This podcast is entirely AI generated. Scripts by Claude Sonnet 4.7. Voiced by Qwen 3TTS. Not affiliated with Hacker News or Y Combinator. Now go build something that's yours. We'll see you back here tomorrow.